Hello, this is Teach Nichols, and this video is on circuit variables for AP Physics. The essential question is, how can I describe and explain what is happening inside a circuit with variables? Hopefully you recall from your introductory physics class that there are four primary variables that we use to describe and explain what's going on inside a circuit, and those four variables are voltage, current, resistance, and power. One of the tricky things about this unit is really coming to a robust conceptual understanding of what those variables are. And that's particularly hard because they are just sort of different combinations of the fundamental variables we've already learned, which are charge, energy, and time. So all of those variables are made up of different combinations of charge, energy, and time. Together, these four variables will describe how electrons move through a circuit, transferring electrical energy from the power source to the resistor. So we're going to go through these variables one at a time. The first one is voltage. From the last unit, you should know that voltage is defined as energy per charge. In this unit, it means the same thing. I mean, it's the same variable. And we have the same units, which are joules per coulomb or volts. And you can also think of it just as like how much energy each coulomb of electrons has in your circuit. Battery, being the energy source in this picture, provides energy to those electrons by pumping them into a state where they are closely packed or located close to each other. And if you read a statement about that battery, such as the battery supplies 60 joules of energy to 4 coulombs as they pass through it, you ought to be able to use that information to infer that the variable that they're telling you about is voltage, and the voltage for this particular battery would be 60 over 4, or 15 joules per coulomb, or 15 volts. So this is a 15-volt battery, and every joule of every coulomb of electrons that pass through will gain 15 joules of energy. If you build a circuit, it is often useful to have ways to measure the voltage that is either gained by the electrons as they pass through the battery or lost by the electrons as they pass through resistors. We will use a tool called a voltmeter, occasionally called a galvanometer, to do this sort of voltage measuring. You may have seen these things before. Sometimes they're in a tool that has lots of other things it can read. So the voltmeter is just one setting in that tool called a multimeter, but we'll be playing around with that in class. When you see a voltmeter in a circuit diagram or schematic, it will look like a circle with a V in it, and that V, of course, indicates that it is a voltmeter. The probes on the meter that you have, the red and black wires coming out of the meter, don't actually measure the electric potential. All they can measure is the difference in electric potential from one side of the wire to the other. So they can't tell whether what the absolute potential is compared to infinity, because they don't have a way to be at infinity. But what they can tell is what the change in potential is from one wire to the other. So voltmeters actually only ever measure delta V between the two leads. Since the voltage increases of the electrons at the battery as they are pumped closer together, and decreases or is used up at the resistors because we allow the spacing to spread out between those electrons as they pass through the resistors, usually you'll have one probe on one side of the battery and the other probe on the other, or one side of the resistor and the other side of the resistor. So when you connect a voltmeter, it should look in your drawings like that figure shown below, where it's sort of straddling the object that you're interested in learning about the voltage from. This particular voltmeter would measure the voltage lost at that light bulb. Incidentally, this is also going to measure the voltage gained at the battery, because you'll see that those leads are also touching the two sides of the battery. The wire path is a little bit longer, but there's no other resistors in there in the way, so this voltmeter would measure either of those things. Should be the same. So the second circuit variable is current, and current is represented by a uppercase I in equations. Current is essentially the flow rate of electrons. Note here, this is not the speed or the velocity of the electrons, it is how many electrons every second pass by a location in space. And as such, the units of current are coulombs every second, but we sometimes call this an ampere or an amp or just A. There is an equation on the equation sheet that shows this definition. Current is defined as the change of charge, so the number of charges that pass by every second. So if you forget that definition, you could look it up, but really this is something that you should sort of know. So in this diagram shown below, right, if you imagine positioning yourself at the bulb or at the battery and essentially counting the number of coulombs of electrons that go by every second, you would be figuring out the current. For example, if you knew that in 120 seconds, 30 coulombs of electrons pass through a resistor, you would be able to calculate the current at that resistor as being 0.25 coulombs per second or 0.25 amps. A funny note about current. We all know that electrons go out of the negative side of the battery and up and around back to the positive side of the battery. But when they first made all these groundbreaking discoveries about circuits and electrodynamics, they didn't know what an electron was. They didn't know what was moving, which particle was moving. And so they defined particles as positive and negative, and they said, let's just, I guess we'll make the positives move, because they couldn't actually see what was happening at a subatomic level. We have Benjamin Franklin to blame for that. So Benjamin Franklin decided that this word current was going to refer to the flow of positive charges. Positive charges don't flow, it turns out, but we've never fixed it. And so the direction that we will define current, or if you see any arrows in a diagram that say current is this way, that's actually opposite from the direction the electrons are actually moving. It's like the direction an imaginary positive charge would be moving, but it turns out they're stuck in the nucleus. So the direction of current is opposite from the direction the electrons are actually going. Hipster electron goes against the current. Measuring current is really straightforward as well. You use a tool called an ammeter, not amp meter, but ammeter. And it is probably on that same device that we measured voltage with. In a circuit diagram, an ammeter is a circle with an A inside of it with two leads or wires coming out of opposite sides. But one very important difference about ammeters is that in order to measure current, you have to actually essentially allow the current to flow through the ammeter device. And that means that you have to attach the ammeter into a circuit so that all of the electrons have to go through the ammeter before they go through whatever device you want to measure if you want to know what the current is. So this is a different kind of connection than voltmeters, and they often like to test whether you can figure out where to attach these things to actually measure the values that you're interested in. If you try to attach your ammeter like as shown in the diagram to the right, what happens is it's not going to measure the current through the resistor because all of the electrons going through the ammeter are avoiding the resistor, they're going around it. So we don't want to hook up ammeters the way we hook up voltmeters. Your third circuit variable is resistance, which is represented by a capital R in our equations. The units of resistance are super ugly. It's a joule second per coulomb squared. I don't even know. I don't have a conceptual understanding of what that means. But we abbreviate this or shortcut this as the ohm, which is represented by the Greek symbol omega or upside down horseshoe. The resistance of a circuit roughly describes how difficult it is for the electrons to pass through a part of the circuit, or how much energy it takes to force electrons to go through the circuit, and is a material property. It depends on the way that the resistor or the wire or whatever you're trying to flow electrons through is designed. We're going to come back to this. There is an equation for resistance or resistivity, just like there was an equation for thermal conductivity. They actually tend to be pretty similar. Objects that allow heat energy to flow through them quickly also allow electrical energy to flow through without much resistance. But in any case, you can kind of see that the resistance of a material is going to depend on a few of the dimensions of the material as well as what material it's made out of. So that equation will be coming up in a future video. But for now, if you know that one object has got a resistance of 4 ohms and another is a 1 ohm, obviously the 4 ohm object has 4 times as much resistance. That means it is 4 times more difficult for the electrons to get through, or it requires 4 times as much energy to get through compared to the lower resistance one. If you want to measure the resistance of a device in a circuit, we will use an ohm meter, which again is often found on this handy dandy multimeter tool. If you were drawing an ohm meter in a circuit, it would look like a circle with an ohm in it with two wires coming out the sides. And the probes on the ohm meter are going to measure the resistance in the device in between the leads. You will usually or exclusively hook up an ohm meter the same way we hook up voltmeters, which is that the probes basically touch the two sides of the object that we are interested in knowing the resistance for. So I saved the most important variable for last. The last variable is power, which is written usually with a kind of a cursive P or a little bit of an italics P. And power is the most important unit because it tells how much total energy is transformed from one type into another every second, or work per time, work every second. This is relevant because usually the point of a circuit is to get energy out, right? To put electrical energy in and make it do something, whether that something is sound or light or heat or whatever it is that the thing you've got plugged into the circuit is doing. We want to be able to control how much of that energy is transformed, how much sound or light or heat is coming out of the circuit. And the variable that ties most directly to that is power. It tells you how bright the light bulb is or how fast the motor is spinning. The units of power are going to be the joule per second, which is units of work per time. But this is also known as a watt, which is capital W. So for example, if you knew that over the course of 30 seconds, 90 joules of electrical energy was turned into light at a light bulb, then the power would be 3 joules per second or 3 watts. If you look at these two circuits that are set up, you can clearly see that the light bulb on the right is brighter than the light bulb on the left. That is a clear indication that there is more power at that light bulb. It does not tell you whether there is more current or more voltage. An important note, okay? All it tells you is power, and we will learn how to calculate power in another video. There is not a handy-dandy power meter that you can plug in, so you have to actually measure other things and do some calculations to get power. Okay, thank you for watching. Please take a minute to revisit your essential question, which is how can I describe and explain what's happening inside of a circuit in terms of variables, and read this little Calvin and Hobbes I have for you. Thanks for watching.